Knowing the form of the ideal gas law, we should be able to make qualitative predictions of what happens to the measured quantities as one of them is changed. Part of doing so is knowing which quantities change and which don't, given a certain experimental setup. We'll see how changes in moles affect volume, how changes in volume affect pressure, how changes in temperature affect pressure, how changes in moles affect pressure, how changes in pressure affect volume, and how changes in temperature affect volume. Let's start with a simple relationship. I've got this balloon. Let me blow some air into it. And let's think about what's going on inside here. What about the temperature? It's essentially room temperature, a little bit greater because the air came out of me, but it's essentially room temperature. It's got a volume. We could measure it by displacement of water if we had the right setup. It's got some number of moles of gas in there. And it's got a pressure. But what about the pressure? Well, pressure is a result of molecules pushing out on the surface. And the molecules inside pushing out are balancing the molecules on the outside pushing in. So essentially, it's 1 atmosphere pressure inside here. Not exactly. We know the elasticity of the balloon makes it slightly higher pressure inside here, but it's essentially 1 atmosphere. What if I blow another breath in here? What's changing? Did the temperature change? No. Did the pressure inside here change? No. Again, the pressure inside and the molecules inside are balancing the pressure from the molecules outside. Number of moles changed and volume changed. Number of moles and volume must be directly proportional, and they are on the opposite side of the PV equals nRT relationship. In blowing up a balloon, pressure and temperature inside the balloon stay constant. Since N and V are directly proportional on opposite sides of the ideal gas law, an increase in the number of moles of gas causes an increase in the volume. I have here a syringe which is hooked up through a piece of tubing to a pressure gauge. This will allow us to see how changes in volume can affect the pressure of a gas. So we have about 25 milliliters of air in the syringe and another 5 milliliters of air in the green tubing that connects the syringe to the pressure gauge. Pressure gauge is currently pointing at 15. The units there would be pounds per square inch. And if I push in the barrel of the syringe, am I changing the temperature? No. Am I changing the number of moles of gas in the system? No, it's a closed system. So I would be changing the volume, and the pressure should respond. So if the volume goes from approximately 30 milliliters total down to 25, down to 20, down to 15 milliliters total, we've approximately halved the volume and we've doubled the pressure. And if I let go of the barrel of the syringe, it will slowly get pushed back out and the pressure slowly comes back down. In pushing in the barrel of the syringe, the number of moles and temperature inside the closed system stay constant. Since P and V are inversely proportional on the same side of the ideal gas law, a decrease in the volume of gas causes an increase in the pressure. So we've got our pressure gauge again, but this time instead of being hooked up to the syringe, it's hooked up through a piece of tubing to this aluminum ball. And I've got this beaker of water on this hot plate that's very warm. So let's see what happens with the pressure and how it responds to temperature. We have the ball hooked up directly through this tubing to the pressure gauge, which again reads 15 psi, which is essentially 1 atmosphere. Now it's a closed system, so the number of moles is not going to change in here. And the ball is not going to change its volume. But if I put it into the hot water, let's see what happens to the pressure. I'm going to plunge it in. Pressure starts at 15 psi, going up to 16, heading towards 17, you might say it's going from room temperature to maybe 50 or 60 degrees C in this hot water. How come the pressure isn't tripling? Well, keep in mind, on the Kelvin scale, that's not a very big change percentage-wise. If I take the ball back out of the hot water, it should cool back down, and slowly the pressure should go back down. In plunging the metal ball into warm water, the number of moles and volume of the closed system stay constant. Since P and T are directly proportional on opposite sides of the ideal gas law, an increase in the temperature of the gas causes an increase in the pressure. Now I have my balloon inside this heavy-walled glass jar, and the jar sits on a plate, and out the back of the plate is some tubing that goes down underneath into a vacuum pump, which you really can't see. Now when I turn on the vacuum, we're going to remove gas from the glass jar. The number of moles of gas will go down. Now, we're not going to change the temperature. We're not heating it up or cooling it down. Hopefully the volume won't change. So if the number of moles goes down, the pressure inside should go down. Now, the balloon in there is a closed system, not changing the temperature, not changing the number of moles. But remember, the pressure inside responds to the pressure outside. So if the pressure outside decreases, the pressure inside should decrease as well. So let's turn this on. Close the tap at the top, and now we're sucking air out of the jar. Number of moles goes down inside the jar. Pressure goes down inside the jar, which means the pressure goes down inside the balloon as well. Since N and T of the balloon can't change, the only thing that can respond is the volume. Can you see the balloon? Volume is increasing because the pressure inside is decreasing of that gas sample. It's going to continue to get bigger. We hope the balloon can take this stress. And once it completely fills up the volume of the gas, we can't suck any more gas out of there, so we'll turn it off. Open the tap at the top. Now we're putting gas back, or air back in. Pressure is increasing not only in the jar, but also inside the balloon. As the pressure increases inside the balloon, the volume decreases. And it should now go back to its original volume. In pulling a vacuum on a jar by sucking the air out with a vacuum pump, the temperature and volume of air inside the jar, at least at the start, stay constant. The volume eventually changes some as the balloon expands, but let's consider what happens at the start. Since N and P are directly proportional on opposite sides of the ideal gas law, a decrease in the number of moles of gas causes a decrease in the pressure. The balloon in the jar expands in response to the change in pressure in the jar. The number of moles and temperature inside the closed system, the balloon, stay constant. Since P and V are inversely proportional on the same side of the ideal gas law, a decrease in the pressure of gas inside the balloon, which mirrors the pressure outside the balloon in the jar, causes an increase in the volume. To see how temperature affects volume, let's look at a video from the internet. In the middle is a flask of liquid nitrogen. Now, liquid nitrogen is extremely cold, 77 Kelvin, minus 196 degrees C. Notice he's using gloves and forceps to handle these balloons and put these balloons down into the liquid nitrogen. Again, balloons are closed systems, so the number of moles of gas inside the balloon is not changing. The pressure inside the balloon, again, reflects the same pressure that's outside, so it's staying at 1 atmosphere inside. But as the air inside the balloon gets extremely cold, its volume goes way down. And when he takes the balloons back out, they come back to room temperature. As the temperature increases, the volume increases, and they should come back to their regular size. In plunging the balloons into liquid nitrogen, the number of moles and pressure of the closed system stays constant. Remember that pressure inside the balloon mirrors the pressure outside, which stays 1 atmosphere. Since T and V are directly proportional, on opposite sides of the ideal gas law, a decrease in the temperature of the gas causes a decrease in the volume. In summary, we find that when two items are on the same side of the equation, they are inversely proportional. When one goes up, the other goes down. When two items are on opposite sides of the equation, they are directly proportional. When one goes up, the other goes up, or when one goes down, the other goes down. We should be able to make qualitative predictions using the ideal gas law if we can decide what stays constant and what changes.